Jeffrey Newmark, the IRIS program scientist from NASA headquarters in Washington. And Alan Teitel, the IRIS principal investigator from Lockheed Martin's Advanced Technology Center Solar and Astrophysics Laboratory. And we'll begin first with comments from the NASA Ames Center Director, Dr. Pete Worden.
Thank you, George. This is an incredibly exciting mission. I'll let Dr. Teitel tell you a little bit about the details of the science, but from our perspective at NASA Ames, there's two really important points. The first one is that this is a low-cost mission. It's a small explorer, and it demonstrates I think the wave of the future, that we're going to be doing a lot more with lower cost, smaller missions, at the same time getting really earth-shaking science. As I think you'll hear, this is the first mission that will really tell us the detailed physics that's going on at the solar surface in the atmosphere above it. It's also a real opportunity to interact with computational work. NASA Ames is the center at NASA that has the agency's supercomputer, and we are able to work the computer with the data we have to really understand what's going on. In fact, that work's been going on for several years, so we're very excited about that. The second key point, though, is that the sun is increasingly important to our environment. And as those of you that were listening a little earlier saw the effect of power outages. Well, we believe that some, maybe a lot of power outages, actually have a lot to do with solar activity. So the better we can understand the physics going on, the better we can understand that activity, the better that we could potentially predict and mitigate some of these problems. So it was sort of, in some sense, unfortunate to delay the launch, but it's also fortuitous to highlight the importance of this mission. Thank you.
Thank you, Dr. Worden. And now to Jeffrey Newmark, the IRIS program scientist from NASA headquarters.
Well, thank you. I'm very pleased to be here today to introduce the science of IRIS. IRIS is our newest member of our heliophysics fleet, and I hope to, by the end of this press conference, you'll get an idea of the exciting science that we were doing in heliophysics. I should step back and say, what is heliophysics? Heliophysics is the oldest science known to man. It's the study of the sun, and it's also the newest science. It's the studying of its interaction with the Earth, our technology, and the rest of the planets throughout the solar system. If you could show me the first video. Most people think of the sun as a constant source of heat and light that bathe our planet. This is how we see the sun, though, quite different than a constant source. You see here images of the atmosphere of the sun, the outer atmosphere of the sun, and you see the tremendous amounts of activity that is going on throughout these video. I should point out that everyone, when we see these pictures today, people think of computer graphics. These are real images taken from our current spacecraft. These are not generated. So all the movies I'll show you today are real images. What we're seeing here is the sun is a giant, huge nuclear fusion reactor. At the center, it is tens of millions of degrees. And over 500,000 miles as it goes outward to the surface of the sun, it slowly cools. And where the surface is about 10,000 degrees. Then something very strange and mysterious happens. In the next just a couple of thousand miles, the temperature rises again in the outer atmosphere to, again, millions of degrees. What causes this rise? How does the energy transfer from the surface, the cool surface, to this hot outer atmosphere? This is the questions that IRIS, the science of IRIS, is going to address. One might ask, why do we care about the sun? What are we going to learn? Haven't we seen a number of these graphics before as we see these images? Can't we explain it from just this? And as I hope to show you that no, there is more to be gained. If you look at my second graphic, if you could show the second video. If we step back and we look at the sun now as the small in the center, and we see the larger extended atmosphere of the sun, we see a tremendous display of activity. We see particles streaming away from the sun constantly. This is known as the solar wind. And then we see the solar storms. These were the active parts that we saw earlier on the sun. These are now expanding throughout the entire solar system. The snow-like features you see are actually high-energy particles streaming, hitting our spacecraft and disturbing the cameras. These high-energy particles continue on, and less than an hour later can hit the Earth. These, as Dr. Warden mentioned, these can have effects for us on Earth. They can affect our navigation, our communications, our power systems, and especially our astronauts. Once they leave the protective lower Earth's atmosphere, they'll be quite vulnerable, along with our other systems that leave the protective low Earth. They become vulnerable to these storms that are traveling. So why heliophysics? What are we trying to study? So heliophysics is broken down then into fundamental questions. We're looking at what causes the sun to vary. What are the fundamental physics processes that are going on? How does this variability interact with the Earth and all of the planetary systems? And what are the impacts on humanity and as we explore other worlds? So that is the science of heliophysics. I think by now it's obvious that we have a number of observatories to look at the sun. We've seen these beautiful images. If you could show my third graphic, the question then is, why is a new one? Why are we launching IRIS? IRIS actually fills a crucial gap. We've seen a lot of our current observatories look at the surface of the sun, the photosphere, for instance, where I just showed you in the sunspot. And then we have the full outer corona, the million-degree corona that we see in the full disk. In between this interface region, which you see in the inserts of some of these movies, we currently have just some observatories now that look at without the necessary cadence and spatial resolution and spectroscopy to really unlock those mysteries of how the energy and matter flow, what's driving the solar wind that comes from there. All of that is hoped to be learned from IRIS. All right, and thank you. That's all I have.
All right, thank you, Jeffrey. And now to Alan Teitel, the IRIS Principal Investigator. Alan?
Thank you, George. You've heard so much about the sun, there's not very much left for me to say. What is this interface region? And the answer is we don't know. If it's so important, why haven't we studied it in the past? Well, the answer to that was hinted at by Pete's comments, that the instruments that look at this region in the past have had about 20 times poorer resolution spatially and about 20 times poorer resolution spectrally. And spectrally allows us to measure temperatures, velocities, pressures. So it's important to have spectroscopic information. But basically, we've been looking at things that happen so fast that data taken as slowly as previous instruments have done really hasn't given us any information. But even more fundamentally, there's not been a push to look at this region because the atomic physics in this region is very, very, very complicated. And it's only been in the last decade or so that people have developed computer codes that can do what we hope is an accurate job of simulating these regions. And later in this talk, I'll show you some examples. But the Pleiades computer cluster at Ames has been instrumental in doing these simulations. Over the past 3 or 4 years, we've used about 30 million CPU hours a year at Ames, and a comparable amount on computers in Europe. So with the first slide, let's look where the interface region is. So what you can see in the center is a big yellow ball with little black dots on it. Those little black dots are sunspots. And surrounding it is the corona. And that was a picture taken on the 13th of November of 2012 in Cairns, Australia. So this was last year's solar eclipse. It was a particularly nice view. And so the question that we're asking, or hoping to answer, is how we get from the bright yellow ball, which is about 10,000 degrees Fahrenheit, to the atmosphere above it, which is a couple 3 million degrees Fahrenheit. So if we could have the next slide, please. We now see superimposed the top of the transition region, and that's where it fits. And you can see that it's not completely smooth around at the edges. And that's because there are a lot of three-dimensional structure that protrudes from the surface into the corona. And now we'll show you another movie, but let's hold the movie for a second, and so I can tell you what this movie is. It's a movie of the edge of the sun seen with the Hinode spacecraft, taken about as fast as Hinode can operate, which is about one image every 4 seconds. And what you'll see are a lot of little fine jets, hair-like structures on the edge of the sun. And on the top is the direct Hinode image, and on the bottom is an enhanced image, and you can see the fine central cores of these structures. These structures are about 100 miles wide and about 10,000 miles long. They go about 75 miles per second, and they last about 10 minutes. And we discovered these structures on Hinode and realized for the first time that 4-second exposures and just one wavelength wasn't enough to see them. Also on the frame of this movie is an image of the Earth. And so if we could have this, my first movie. So on the top you see these jets, and on the bottom you can see these very fine central cores. And you can see some of them are as big as the Earth. So they traverse the diameter of the Earth in a time between 5 and 10 seconds. They're really fantastic things. They look like the smallest kinds of things that you see on the sun, but they're the size of the Los Angeles area, going 75 miles a second, which is not quite as fast as you can drive on the freeways in Los Angeles. So if we could have the next movie, which shows the sun over a sunspot. And in this movie, if you look at the bottom, you can actually see the origins of the jets. And again, that's very fast, as the movie is. Now what I'm going to do is show you what we hope we'll see something like. This is a numerical simulation. It's 3 million CPU hours. That means that if everybody in this room, let's assume there are 50 people in this room, let's assume there are 30 people in this room, you all working on your computer for 10,000 years, you could make this movie. Or you could go to Ames and run it in a few hours. Actually, it takes several weeks because you don't get the computer all the time. So if we can have this movie, and this pans over the movie so you can see the three-dimensional structure of the atmosphere in this wavelength, which is on doubly ionized magnesium. So that is just the beginning. That movie is not what only thing you got for your 3 million CPU hours. You got enough information to see what the spectrum would look like. So the next movie shows the first movie head on and moving the spectrograph slit across it and seeing how the spectrum changes. So if we can have that movie. And you can see the spectral changes are very complicated. The spectral line wiggles, it widens, the surroundings get bright and dark, and that all encodes the physics of the process that's going on. And without the interpretation that the computer provides from us, it would be difficult and probably impossible to decode this. So with that, I'll stop and turn it back to George.
All right. Thank you, Alan. And we're ready now for questions. And once again, please give your name and affiliation when you get the mic. And we'll start here with Nora.
Thank you. Nora Wallace, Santa Barbara News Press. Several of us have newspapers that are not oriented towards science. And so I'm hoping that you can explain to our readers why this mission matters to their lives and what IRIS will bring to the average person in terms of knowledge.
Pete hinted at it in the beginning, or maybe not hinted at it. Our primary interest right now is how we take the kinds of discoveries that NASA makes and communicates with society so that the society can interact with what we learn as scientists. Because I'm well aware that all of these complicated details and 3 million CPU hours of computer time doesn't really translate into something that's easily grasped. But what is easily grasped is the sun has massive explosions that put billions of tons of material moving tens of thousands of miles an hour into the Earth's atmosphere. They impact the Earth and they cause problems in a variety of ways. And many of these kinds of problems, as Pete mentioned, we are now learning are not gone. So you had a power system go out in the San Ynez Valley, and as a result of that, as a secondary effect, you had a bus bar fail in a transformer at Ames. In the motel that I'm staying at, there was a fire truck in front because when the power went out, somebody got stuck in an elevator. We live in a very, very complex society, and the sun has a very important role to play in it. So people like myself look at what may be perceived as tiny details, but are in fact the engine that runs this system and the engine that fails sometimes.
If perhaps I could add a little bit there. The field of heliospheric physics is often known as space weather. And it's very similar to weather in many ways. And if you can think of a hurricane, for example, the hurricane can have dramatic effects. The number of hurricanes may be related to climate changes and so forth. But in order to understand what's going on in that hurricane, you have to understand the detailed physics of it. So you have to understand how the heat comes off the ocean, how it interacts with the atmosphere, how the hurricane starts. In fact, there's an old statement that says that it was a butterfly wings flapping in Africa that started the hurricane. And that's sort of what we're getting at here. The sun dominates everything in the solar system. It dominates our climate. It dominates our weather in many respects. So this is an important piece of understanding, if you will, that butterfly wing and how we can make those predictions that in the end will help us understand power outages that we don't understand changes to the Earth's climate, some of which are due to influences of the sun, some of them are due to perhaps human influences, and a lot of different factors. So this is really ultimately about us and about how that object that we see in the sky every day affects it.
Any further questions? Janine.
Janine Scully, Santa Maria Times, Lompoc Record. You're talking about some cool science, but you guys don't seem too excited that you're, I guess, now 2 days away from launch. How excited are you to get this mission underway so you can get this information?
We're not excited, we're terrified. A mission like this starts 5 years ago. Hundreds of people have worked very hard. But in the end, we're flying it on a device that's surprisingly reliable. But ultimately, it's in space. It's a difficult, complicated environment. Lots of things can go wrong. And it's a mistake ever to be too optimistic. You have to look at every downside. We've just spent the last couple of days looking at all the way things can fail. So it puts you in a sort of mood that, you're not crossing your fingers. You're really prepared, but you're also prepared for the fact that this is not something that just happens. This is something that's only the result of a lot of hard work. It'll be exciting when the door opens and we get science and we see that everything we've thought about really had come to roost and we get good data. But until then, it's more apprehension than science.
I'd just like to add, not only, I agree with Alan, and also I think one of the most exciting parts is not answering the questions that we know. It's the new things, the discoveries that I'm positive IRIS will bring us. Every time we've looked at the sun in more detail than we ever have before, it opens up a new window for us. And I think that's the most exciting part is the things that we don't know.
Nora?
Nora Wallace, Santa Barbara News Press. When this information becomes available, is there any way to quantify for us the amount of data that you'll be receiving, and also who are the anticipated users beyond yourselves?
Okay. We know exactly how much data we get. And this, like all the other heliophysics experiments, are available to all in near real time, which means usually within a few hours and sometimes within a few minutes. But they're available to all the scientists in the world, and in fact, anybody who wants to use the data without any restriction whatsoever. And we have websites that you can log on to. You can learn how the experiment works. You can learn how to operate the experiment. You can even learn how to propose to do experiments on the experiment.
Right. Additionally, of course, there's the science data that the science community will be looking at. But there are, as Alan mentioned, the real-time movies. There's real-time data that normal citizens, everyone can look at. And in the movies that I showed and Alan showed, a lot of those are, people look at them all the time. We have the statistics on the web that people are captivated by the beauty and that this tremendous star right next to us is what it's doing. And so this data certainly will be available to all.
Yeah, and I might add one of the most important target audiences for this data, of course, it's the scientist. I'm a co-investigator on it, and I can't wait to get my hands on it. But this is really data that will help us get the next generation of students and young people excited about the sun, of how it really dominates everything we do. So there's a very active program to make this data available to students at every level. And so we're pretty excited about what we can do with everyone. And if you have children, we hope that they'll be bringing some of this home and showing you what they're thinking of.
Any further questions? All right. Do we have some from Twitter or online?
Hi. Questions from social media. The SDO AIA instrument views the full disk of the sun. How much of the sun, or what percentage of the sun will IRIS look at?
Just a few percent. It has a very small field of view, about 40 arc seconds compared to 1920 that AIA has. And the reason is that we have higher resolution and higher cadence than AIA, and we don't have a geosynchronous orbit which allows us to communicate 24/7 like AIA has, and so we have to have an onboard memory and download our data 13 or 14 times a day to ground stations in the polar regions. But it's an important, interesting experiment. that fills in a niche between AIA and Hinode.
Okay, thank you. Tell us again when that data will be available.
We open the doors 21 days after the 28th. And I imagine for a couple of weeks we'll be doing all kinds of calibrations. But when we open the doors on AIA, we saw one of the most spectacular events that we've seen in the entire mission, and that was broadcast all over everywhere. And if we see something spectacular on day one, it'll be all over the web too.
Thank you.
And back here, any further questions? All right, in that event, just a programming note. There is no change to our NASA TV schedule on Thursday, the 27th. We will start our live coverage of the L-1011 departure at 6 p.m. Pacific time. That's 9 p.m. Eastern time, and we'll continue through spacecraft separation. And that will conclude our mission science briefing, as well as our pre-launch news conference. And thank you very much for coming.
So you take pictures of the sun, right? Well, that's cool. Can you show me one? What do you mean, no? They can't be that big. Come on. Hey, where'd you... Wow. That is kind of big, isn't it? Does anybody have a truck?